the y of the second.
Okay, so we are going to be going over acceleration today. And most of what we go over today is going to feel familiar, I hope. It should be, because all we're going over today is really what you learned about acceleration in Science 10. If we're really lucky, we might get to one new formula, okay, that we use for acceleration. All right, so we need to understand what accelerated motion is. What is something doing if it's accelerating? Don't say accelerating.
Going faster.
Could be going faster. Could be going slower. Acceleration is any change in, starts with V, velocity. Okay, that's the definition of acceleration. Any change in velocity over time is acceleration. That's where this formula that you learned last year comes from. Okay? Acceleration is the rate at which you change your velocity in meters per second, or meters per second squared. All right? So that's what you learned last year. Okay? The definition of acceleration, you learned that formula, you learned how to solve problems and manipulate that formula with algebra. Okay? That's all Science 10. We're going to review that today and hopefully get to some of the other formulas. There are 4 more, okay, that deal with acceleration. Okay? And we're going to use them all multiple times in this course, especially when we get to projectile motion, okay? Which is incidentally the last thing in this unit. Speaking of the last thing in this unit, I don't know if I told you guys this the other day, but your unit exam date is set, March 14th. Okay, will be your unit exam. That's 2 weeks from tomorrow. Okay, something like that. Right, so just be aware that's when that's going to happen. Okay? All right. So, whenever the velocity of an object is changing, it is accelerating. We do not use the term decelerate in physics. Okay? Acceleration can be positive and it can be negative, but we don't use the term decelerate. Okay, so any change in velocity is an acceleration. Okay. Now, uniform acceleration is what we mostly deal with. Okay? And uniform acceleration means that if I drew a velocity versus time graph, the object would go like this or like this. Okay? Either way, the line, it would be linear. Okay? That's uniform acceleration. The object's velocity changes by the same amount every second. Okay, everyone okay with that? Now, given that idea, okay, that these lines are in fact linear lines, and on this axis is velocity, and on this axis is time, what would the slope of that line represent?
Displacement.
Not displacement. I can get displacement from that graph, though. It's part of that graph. Acceleration. Okay, here's why. Okay, if we think back to graphing, and I'm looking at this graph, it would have an equation that would look like this. Everybody okay with that? Right? It's a linear function, so y equals mx plus b would apply. All right. If I solve for m is going to be y minus b divided by x. All right, so here's y. Okay, is it a velocity? Right? And not only is it a velocity, it would be the final velocity, right? It's the last one on the line. Agreed? Okay, so if y is final velocity, what would b? Initial velocity. It's the y value when x is 0, right? At time 0. So b would be vi. What's on the x-axis? does that formula that solves for slope solve for acceleration as well? Okay, very similar to the position time graph one, right? When we found the slope of a position time graph, we found it was velocity, the rate of change of position. On a velocity versus time graph, the slope is the rate of change of velocity, acceleration. Okay, everybody all right with that idea? Okay, that's something you learned last year in Science 10. Okay, we did a lab on that if you were in my class, okay, in Science 10. All right, so that's where this formula comes from. Okay, that formula you used back in Science 10 calculates the slope of a linear function for an object whose velocity is changing constantly. Okay? All right, and that gives us the proper units for acceleration, because on the top of this equation, I would have meters per second, and I would be dividing by seconds. Meters per second tells me how much faster I'm going every second. We usually just say meters per second squared. Okay? Everyone all right with that? Is that ringing a bell from last year? I hope so. Okay. All right, so let's say I've got this fairly simple example here. I've got this fighter jet, and it starts from rest. What does that mean?
Initial velocity.
Initial velocity is what?
0.
0. Okay? If something starts from rest, initial velocity is 0. If it comes to rest, which would be 0 then? Final velocity. If it comes to rest, that means it's slowing to a stop. It's coming to rest. Okay? So starting from rest, VI is 0. Comes to rest, final velocity is 0. Rest always means not moving. Okay? And if you're not moving, your velocity is 0. So in this particular situation, they're telling us the initial velocity is 0 meters per second. Okay? It accelerates down the runway for 29 seconds and reaches a final velocity of 72.2 meters per second. Okay? Can I find the acceleration of the plane? Right, I've got VI, VF, and T. This is the only formula on my formula sheet that has those things in it. Right? Incidentally, this is where using your formula sheet is going to become super important. You have 5 formulas in the kinematics section of your formula sheet that involve acceleration. Okay? The way you determine which formula to use is by writing out your givens. Okay? You look at your givens and you go, okay, I've got these things and I'm looking for this, I use this formula. Oh, this time I've got this combination of givens, now I'm going to use this formula. Okay? So now that I know that, all I have to do is plug in my numbers. VF was 72.2 minus 0 divided by 29 seconds. Okay, and if I do that, right, I should get 2.5 meters per second squared. Okay, and it would be positive because the plane was moving forwards in the diagram. Okay, everybody all right with that? Okay, is that a very big acceleration? 2.5 meters per second squared? It's not. Okay, that's not a terribly fast acceleration. Would you feel that? Yeah, if you were on the plane, you'd be pushed into your seat a little bit, but no more than if you were in a friend's car and they're, kind of heavy-footed. Okay, if somebody was to floor it in a car, you'd probably be pushed into your seat harder than that. Okay, that's about 1/4 of a G. Okay, right now you're experiencing 1 G. Gravity is pulling on you, and that acceleration is 1/4 of that. All right, so here's a look at some of the other formulas that we're going to use. So we got that first formula, which is our old Science 10 formula, delta V over delta T. Okay, then we've got the 2 formulas there that involve displacement. Okay, solving for displacement when I know acceleration and time and one of the velocities. And then I've got the one that doesn't even involve time. Okay, it comes in handy during projectile motion. And then the last one there, we don't use it very often because the acceleration absolutely has to be uniform for it to work. Okay, we'll go over that one in a minute. All right, so the first formula there, okay, solves for displacement. If I have a velocity versus time graph that looks like this, how do I find the displacement? Anybody remember from Science 10?
Find the area under the line.
Right, find the area under the line, okay? Most people just memorize that, but, okay, realistically, we want you to understand where that comes from, okay? When we find the area underneath this line, we are essentially looking at two different types of motion. We're saying if the object didn't accelerate, it would move at this velocity for the entire time. Okay? And then I would just go v times t, and I would have this box. And then I would have this triangle above it, okay, where instead of using just v times t, I would have to find the average velocity, because the velocity is changing from this value to this value, okay? The average velocity would be halfway between, and then I would go base times height divided by 2. That would give me the average velocity. Then I'd add them together. This formula does it all in one sweep. Okay? Would this number here be VI? Right? We already said that, right? That's our initial velocity. It's how fast the object's going at time 0. So if I multiply that by time, am I going base times height for this rectangle? Okay, so this part calculated that area. The 1/2 AT squared calculates that area. You add them together, you've got the area under the line. In other words, the total displacement of the object. Okay, everybody all right with that? That's where that formula is derived from. Okay, now, similarly, this formula here looks at this from the other point of view. It uses VF. Okay, so VF would be way up here, would you agree? Okay, so if I go VF times T, I'm calculating that whole square or rectangle. Yes? All right. Then it subtracts 1/2 AT squared, which we said before calculates this triangle. Well, does it also calculate that triangle? They're the same, right? They're similar triangles. So if I calculate this box and then I subtract this triangle, am I left with the same area that the other formula calculated? I am. Okay? This is just one you use if you have VF instead of VI. Okay? But it calculates the same thing from a different perspective. Okay? But they're both calculating the area under the line on a velocity time graph, which we learned in Science 10 is the displacement of the object. Okay, VF squared equals VI squared plus 2AD. Right? Not really a graphing formula per se, okay? But this one is nice if you don't know how long the object has been accelerating in terms of time, but you know how far it went while it accelerated. Okay? Then you can use this formula. It's nice because it doesn't involve having to have time. Okay? And then the last one, okay, is saying displacement equals VF plus VI divided by 2 times T. What do you suppose that calculates? The VI plus VF divided by 2.
Average velocity.
Yep. Isn't that how you calculate the averages of most things, right? You add the things together and divide by the number of things you added. Okay? So when I add the final velocity and the initial velocity and then divide by 2, I'm calculating average velocity. So all this formula is really doing is this. It's really just V equals D over T. Okay? It's just written out differently to account for the fact that you might know what the final and initial velocities are. Okay? So we're going to look at different ways that those formulas come up. We're going to look at how to manipulate all of those formulas and then solve problems with them. That's today and tomorrow and probably Friday. Okay? And then we'll look at doing a lab probably next week. Okay? I want you to write this one down, and then we're gonna look at how we would solve it together, okay? So I'll give you a minute or two here to get it written down. Okay, so this is another one of those questions where you gotta read through the context of the question and get everything you need from it, okay? So I have this hybrid car with an initial velocity of 10 meters per second east. So that's my first given, okay? VI, 10 meters per second east, okay? It accelerates at 3 meters per second squared east. There's my second given. East, okay? How long will it take? What do they want me to find? Time. To reach a velocity of 25 meters per second east. So that's VF. Okay. Do I have a formula that has those four things in it on my formula sheet? Okay, it's this one. All right. I need to find time. So do I need to manipulate that formula? Okay, so if I want to get time by itself, what do I do with time? Multiply it over to the other side. I don't want to leave it here because it's on the bottom of the equation, and we already know we can't solve for something if it's on the bottom. So I'm going to multiply both sides by time. Time comes over here. Then what do I do with A? Divide by. Yeah, bring it over to this side. All right, so T is going to equal VF minus VI over A. Right, now I just need to plug in my numbers, and I'm set for calculating time. So that'll be 25 minus 10 divided by 3. So 25 minus 10 is 15. 15 divided by 3 is 5 seconds. Okay, everybody all right with that one? Okay, let's look at the other manipulations of that formula. Now, I'm going to caution you here because sometimes people do this. Do not copy down all the manipulations of this formula. Okay, you don't get your formula sheet for the exam. I give you a fresh one. So if all you've done is copied down all the manipulations of every formula and then just gone back to find them, you will be so out of luck on the exam. Okay? You need to be able to do your algebra and do your manipulations. Okay? All right, so we've already shown how this one gets manipulated for time. How would I manipulate it if I wanted to solve for VF?
First you have to bring T to the top.
Right, first I've got to multiply both sides by time. Time's not attached. Remove what's not attached first. Okay, so I've multiplied both sides by T. T's now over here. Now what?
You add VI.
Add VI to both sides, right? I do the opposite. Right now I'm subtracting VI. I need to get it over here. So I'm going to add VI to this. Now I'm solving for VF. Okay, everybody all right with that? Okay. What if, instead of doing that, I wanted to instead solve for VI? Okay, would my first step still be the same?
Yeah.
Move T first, okay. Whoa. Erase. Okay, I want VI by itself. What should I do? Add
to the other side.
Add VI?
Yeah.
Yes.
Yeah.
Okay, there's two ways to do this. I would recommend you add VI to the other side. Now right away some people are going to go, I'm trying to isolate VI. Why would I move it over to the other side with all the other stuff? Well, here's why. If I leave VI over there and move VF, VI is negative. The negative stays there. Okay, and when we start dealing with vectors, okay, if I'm giving you east and west, and then you calculate something when you're done, you forget that what you solved was negative, you're going to say west when it should have been east. Okay, I do that all the time. I know my limitations, so I always move VI over by adding it so that it becomes positive. Okay? Now, how do I move TA over to the other side?
Divide by TNA, like divide VI by TNA.
What am I doing with TNA right now? I'm adding them. Okay? Here's why this works. Think order of operations. Would you multiply T times A before you added it to VI? Right? You do multiplication and division first, right? So that's really just one number. It's like VI plus X. Okay? So I want to move that over to the other side. I'm just going to subtract it. Okay? So I'm going to have VI equals VF minus T times A. Now, if you're a logical person, let me explain why this formula works. Okay? A minute ago, we did this and we solved for VF. And we said that that was going to be VI plus T times A. Okay? T times A calculates the change in velocity. So if I take the change in velocity and add it to the initial velocity, I should get the final. Would you agree? Okay, so down here, if I take my final velocity and subtract the change, I should get what I started with. Right? It's like if you start out, you go to work today after school and you only have $5 to your name. Okay? But you work for a few hours and you make $50. How much money do you have? 55. Okay? But if I told you at the end of the day you had $55, but you earned 50 during the day, would you just subtract that to figure out what you started with? It's the same idea. Okay? Now, if that all didn't make any sense, but manipulating it and just doing math did, forget everything I said and just do the math. Okay? If doing the math didn't make sense, remember what I just said. All right. Try those two. The answers are there. Okay? I'll make them a little bit bigger here. Try those two. They both involve that formula. Anybody remember how you convert kilometers per hour to meters per second? Because you can't obviously use kilometers per hour with meters per second squared in seconds. Okay? Your units all have to match. So here's what you do to make that conversion. So if I've got 20 kilometers per hour, okay, and I want to convert it to meters per second, I've got to convert the kilometers to meters and then the seconds to hours. Right? So what I do is I do what's called the compound conversion. So I'm going to show you the long way, then I'm going to show you the shortcut. Okay? So first, I want to convert the kilometers to meters. Okay? So to convert kilometers to meters, I know that I'll have to multiply the kilometers by 1,000 because there's 1,000 meters in 1 kilometer. Agreed? So 20 kilometers is 20,000 meters. All right, when I do that, the kilometers are going to cancel. Okay? The other thing I have to know is how many seconds there are in an hour. How many seconds in an hour? Don't say 60. Ooh, I stopped the knee-jerk reaction. How many seconds in an hour?
3,600.
3,600. 60 times 60. 60 seconds in a minute, 60 minutes in an hour, 60 times 60. Okay, so in 1 hour, there are 3,600 seconds. That'll get rid of my hours. So really what I'm doing is I'm taking 20 over 1 and I'm multiplying it by 1,000 over 3,600. Agreed? Is there a shortcut to that? If I divide both of these by 1,000, I'm back to this, 20 over 1 times 1 divided by 3.6. It's just a ratio, right? All I'm doing is multiplying by a ratio. What's 20 times 1? 20. Can I just take kilometers per hour and divide by 3.6? I can. That's the shortcut. Okay? If I want to convert kilometers per hour to meters per second, I divide it by 3.6. If I want to convert meters per second to kilometers per hour, I multiply by 3.6. 3.6 is the magic number, okay, when converting kilometers per hour to meters per second. Okay, so there you go. Now you can do number 2, where you have to convert the 20 kilometers per hour into meters per second. Divide it by 3.6.